So I think we'll start the discussion on we have started for is nothing but the overall system accuracy, and that is the uncertainty and the errors that are going to propagate into the system that we started discussing with. It's around 10:05, 4, and only 90 students are there into the meeting. Right. So what we discussed is the errors are going to propagate, maybe because of random source or the systematic source of the error, and we need to find out what will be the overall system accuracy with the more number of components. Right. So it started with a very simple discussion that the measurement of the length of a job or the workpiece into the measurement into the shop floor. Okay, and as per your say feedback that is given, you are well aware with the process of addition of the say errors, subtraction of the error, as well as multiplication and division of the error. So multiplication and divisions are required for the entity measurement, which are derived entities because of two or more number of the elements present in. We also discussed the example. Say for example, area is nothing but the length into width, or say pi by 4 d square, area of a bar, round bar. So in this one, the measurement, there will be two different uncertainties going to be added into the final accuracy of the say final accuracy of the measurement. One. We have discussed this and we have found how the errors will be added. We also discussed one example where the power, the requirement of the power that is given with some equation where there are multiple entities like measurement of the force, measurement of length, measurement of the distance. That is F into L, that is going to make the torque into the speed measurement. And what we discussed is if the final element that is under the study, say for example, there is a n, the quantity is n, which is function of the different individual measurements u1, u2, u3, and so on, then we can find the total uncertainty into the measurement. That will be function of the measurement of the entity plus the very first entity and uncertainty into it, and so on. So where plus minus n is nothing but inaccuracy of the system, and the del u1, u2, and so on will be inaccuracy of the individual components, right? So we can find in the end the total uncertainty, that is say plus minus del n, is equals to the final reading given by the system or the readout minus the measurement of the entities, n number of the elements. Right, so this was discussed, and now we are going to see how this can be combined into the Taylor series. So Taylor series is a very optimal say formulation that can be used for addition of this kind of uncertainties, which are going to give more and more closeness to the true value. That is, so it is going to have better approximation. Now, mathematically, when we consider the terms, we can neglect the terms which are going to be a very small one because of the squaring. So, on neglecting that, we can write the estimated error is equals to the uncertainty into the partial derivative of the function with respect to the uncertainty 1 plus the uncertainty into the second measurement, and say partial derivative of this uncertainty with respect to the particular entity under measurement, and so on. So this is going to give the error that can be there into the measurement. I think it's now 10:05, 10:07. So I will restrict myself. I will not allow the student to join now. Right. So then the relative or percentage error can be found out as del n upon n into 100. That is what is the normal way. Now the standard process for finding the value of EA is we tabulate all the data points with respect to its plus minus errors, say preferably to the second digit of the decimal place. Then we use the equation so that it is treating the overall measurement is function of the individual measurements. Then to find the partial derivative of the function, we take the partial derivative with respect to uncertainty 1, uncertainty 2, and so on. Then we use the numerical values for the data points. Then we compute the equation, compute the total error in the measurement. That is equation 1 that is given in the earlier slide. And then we compute the total uncertainty, and then we calculate the error. So this is the standard process. Let us assume the application of the standard process through the example of the dynamometer. Now the dynamometer is used for the torque measurement, so that we have to consider the experiment for measurement of the torque or the say power by means of the dynamometer. The average power transmitted by the rotating shaft can be found out through this process. Let us understand this. The machine, that is the driven element which is under the test, is connected to the electric cradle dynamometer. Then this is the motor which is taking the power in and generating some torque. Now arm of length L from the center is attached to this, and then there is some element for measurement of the force that is exerted at the arm. Now as the speed goes on increasing, it is going to apply more and more resistance to the motion, and then this resistance to the motion will convert into the force, and then change in the force can be found out, so that the equation that can be used for making the power calculation will be given as, say, simple twice pi nt by 60 in terms of the normal notation in SI units. So it will be twice pi RFL by T in terms of the watts, or if it is given in terms of the horsepower rating, it will be twice pi RFL by 550 T. So this is standard conversion. Now this is depending on the measurement. Let us assume now the time that we have measured with the help of stopwatch, right, when the experiment is started, is giving a measure of 60 seconds, and there is inaccuracy of plus minus 0.5 seconds. So that may occur because of the reason, any of the reasons. Say for example, you have started the motor and then you have suddenly started the stopwatch. When you are going to end the experiment, you have stopped the machine and then you have made the stopwatch at the still condition to take the measurement. Now there is a time lapse between starting and stopping of the watch, taking the measurement, taking the proper reading, and so on. So because of the lag, there can be some error into the measurement of time. See, ideally what we do when we go for the theoretical say calculations in our respective subjects, we do not consider these kind of inaccuracies that are going to be incorporated into the measurements. Say for example, measurement of time duration, you can have the error in measurement of the time. So now, after carrying out number of iterations, we have confirmed that it is mostly equal to 60 seconds as a time for the test, but there is a variation of plus minus 0.5 seconds. Right. Then we have the other parameter to be measured. Say let us say revolution of the shaft. During this 60 seconds duration, how many revolution the shaft has made. Now this revolution might be measured with the help of a mechanical counter, or it can be with the help of say speed measurement device, the one that we are studying in our practical. Say for example, some kind of electromagnetic pickup or a photoelectric pickup. Right. So when we are going to take the measurement, we also have understood that how many errors there can be. Say if it is a contact type of tachometer, we are going to load the instrument, we are going to load the motor. So because of the load step, there is some decrease in the speed, and it will take some time to pick up the speed variation. And at say after a certain point of time, it will be showing equivalent speed or proportional speed. Right. So there may be different errors incorporated into it, so that the number of revolution that has been measured. Now when you go for the speed measurement devices in the latter part of a syllabus, you will come to know that there are different say approaches, different techniques for the speed measurements. So depending on the technique, there may be variation in the error. Right. So this error is present in the measurement of the revolutions, and then that is say equal to plus minus 1 revolution over this time period of 60 seconds. So it has measured after say few iterations, we have confirmed that it is mostly 1202 RPM. That is the RPS revolution made into this particular time, and there is a variation of plus minus 1 revolution. Right. Then similarly, we are going to measure the force. Maybe in here the FPS unit, but there can be error in the force measurement. Say for example, you have used say a spring load, a spring balance for measurement of the force, or there can be some other devices like electrical device or electronic devices based on the resistance change. Say strain gauge based devices are there supposed for measurement. Then there also can be some error introduced. Say for example, after finding and making the assurance, you have found out quantified that it is in the order of plus minus 0.04 pounds. So now you have confirmed that mostly this figure is 12.12 pound, but there can be variation of 0.04 pounds into it. Right. Then the next measurement that you have carried out here, say you have found out for force, you have found out for time, then there is length measurement and the radius measurement. So the arm, the length of the arm into earlier experiment setup, if you recall. Say for example here, the measurement of the length. So from the actual point of contact or at actual point of load measurement device and the true center of the shaft or the setup, that distance is measured say in terms of L, and then that may be measurement with the help of normal steel rule or standard meter tape, or with the help of say more precise device, say for example the vernier caliper, the bigger length or the larger range vernier caliper, and so on. And then after making the iterations, you have found that it is approximately equal to 15.63 with the error of 0.05 plus minus 0.05 millimeters. right? Then the power rating is given as twice pi 550 into 12. This is another standard conversion which can be taken as a constant onwards. So this will be K times FLR by T. Now, as per our procedure, we are going to find the partial derivative with respect to each and every term. So let us take on calculation, we can find the constant, some numerical value for the constant, and then we can find the partial derivative of this horsepower with respect to the first function, let us say with respect to F. And by putting all the values of constant, the length, the radius, the time into this partial derivative, we find this numerically. So this is equivalent to the partial derivative of this term under the study with respect to the function 1 or the component 1, that is with respect to force. Similarly, we have gone for the anticipation of the partial derivative of the second with respect to second entity, that is with the help of radius or with terms of the radius. Then it is again K times FL by T, and then by putting all the values into the equations, we have got this numerical value for the second element. Right? I think now you are able to understand the partial derivative and quantifying that in terms of numerical value. So unit will be here, the SP per revolution, here it will be SP per unit force that is being measured. Similarly, the third one, so it will be KF R by T. So this with respect to the length, and then that will be the power with respect to, or the per inch of the length being measured. Right, then with respect to the fourth term, that is the T. So this will be KFLR by T square, and then we have quantified that numerically. Right, then once we have quantified this, we can find the error, plus minus error will be equals to, say for example, here all the values are known. Say this is the first value, partial derivative into the plus minus error that we have found out. It is say 0.04. Then the second value is, say with respect to the partial derivative, this is the function, second function into, there is plus minus 1 revolution that we found as a measurement error. Right, then the third element, that is the partial derivative for with respect to length measurement, it is here, and we found that there is plus minus 0.5 inch of the error possible into the measurement of length. So to the last parameter, that is with respect to time t. So it is 0.05 is the error, estimated error, and the variation was plus minus 0.5 seconds in the time measurement. So the error is estimated plus minus will be in terms of the power that is being generated. So this is nothing but 0.049, some numerical value found out with respect to the error into the measurement of the power. So the total horsepower that has been anticipated by using notional values without considering any error into this, the ideal value, say 0.905 into 10.12, these are actual measurement that we have confirmed after iterations. So using no uncertainty propagated, we have found the notional value of the power that has been given by the instrument by using a simple equation. So say twice pi, so that is K times FLR by T. So we put the value of F that we have measured approximately after confirmation without considering any uncertainty. So that is nothing but HP rating. Now we are interested in finding the total in uncertainty that has been propagated further. So the HP can be now said as say 3.02 horsepower that can be generated by, or that is generated by the experiment setup with uncertainty of measurement equals to 0.049 horsepower. Right. So this is how we have calculated the or anticipated the uncertainty that has propagated. Right. So this is what is a very precise measurement of the uncertainty. But again, if you see the distribution of the randomness of the error or uncertainty, randomness into the uncertainty, we can understand that that can be considered with 95% of the confidence and so on. So when we consider the individual errors as 95% of the uncertainty that we have computed. The total uncertainty plus minus in the form will be given by a root mean square value. So E, we call that the RMS value. E A, that is estimated error in RMS value, will be the root mean square of the given value. Say the uncertainty 1 into the partial derivative of uncertainty 1 and the square of this term plus the uncertainty 2 and so on, and then we take a root. Now it's very obvious that this is going to cover more band. If you go to the probability distribution function, we find when we consider 95% of the error propagated into the final uncertainty estimation, then this will have a wide error. So definitely the ERMS will be something larger than the earlier error we have predicted by anticipating the actual uncertainty with the help of Taylor series approximation. Right. Then considering the individual errors as 95% of the uncertainty, so total uncertainty for for this example, it will be given as say root of the first term and square and so on that we add. It's a root mean square of the values, so it is 0.29 HP. Now we can compare. It's 0.029 HP with RMS value, and the earlier value it was 0.049. So with respect to this, the root mean square of the RMS prediction is quite larger. That's what I told here into this graph here. Right. Now, this is what we anticipate, but it is not permitted in the actual experimentation. Now let us understand that if we want to establish some theoretical say rule in the experimentation, again we take the same example of anticipating the power from the dynamometer. Now into this, we want that our say generating equipment must be accurate and there should be very less error propagated. Now if it is stated by some constraint, says like your experimentation require that all the measurements should be very accurate and the error should be less than 5%. Right. This is now final error. We know that we want to have this, we should not have error more than 5% or 2% or 1%. But in actual practice, what we anticipated is something else. With the help of most accurate equipments present with us, we have carried out the measurement, we anticipated the uncertainties, and we have seen how those are propagating. So if it is desired that you want to control the final accuracy, we do not have any alternative. So what is done here into the theoretical say estimation of the uncertainty, we can have control over the inaccuracies with all the entity measurement. Say in this case, if I am saying the final error propagated should not be greater than 5%, then I must assure that measurement of the force shall be with the given accuracy. There should be some controlling value for measurement error on the force, measurement of the say revolutions, measurement of the time, and so on. So I must select the proper measurement devices. For length measurement, earlier suppose I use a vernier caliper, but my experimentation is giving a constraint that the total uncertainty should not be more than 5% or 2%. In that case, I must know what shall be the accuracy of my device for length measurement and the diameter measurement and so on. So to know this, what is the maximum permissible error that our instrument or the measurement system for the particular entity measurement is to be taken, can be found out by the other approach, the reverse approach of this. You try to understand this. In the first one, we have taken our general purpose instruments and gone for anticipation of the uncertainty propagation. We have estimated what is the predicted and the say uncertainty that has occurred into the experimentation. Now the reverse way, we are trying to control the accuracy of each and every measurement device used for n number of entity to be measured. We go for the method of equal effects. So into this method of equal effects, what we do is when overall accuracy is required, say just now we discussed, is known, say for example not more than 2%, suppose. So it should be less than 2%. Sorry, the total uncertainty should be less than 2%. Then this is known now, and this is required to determine the component accuracy. That is, suppose there are 5 instruments or 5 measurement systems used for measuring 5 different entities in the experimentation. Then this problem will become indeterminate. We cannot know what shall be the accuracy of each and every individual devices. So to solve this, at say very first instance, we try to distribute this accuracy in equal amounts on all the entities under measurement. Say, as per our equations, now the problem become indeterminate because we are going to find this. This is unknown now. In earlier case, the value of U1 was known because you have carried out actual measurement, and you have found that the error is something plus minus 0.04 time for 0.04 pounds is the, as I say, measurement error into the force, right? So what we do here is we go in the reverse fashion. We allocate the error and then we find the uncertainty that is permissible in that particular entity measurement by using this equation, say del n over say root of small n and then partial derivative of the function with respect to that particular entity under measurement. Say for example here, if desired overall accuracy is known, say for example here less than 2%, I assume 2%, that is known, 2%, say 2% into the total value under measurement, I can find del n. So using this del n, suppose there are 4 entities under measurement. In this case it was a force measurement, length measurement, time measurement and the force measurement there into the measurement of the power. So it means that there are 4 functions. So if I know that this is equals to 4 and the equation relating to this, that is twice pi nt by 60 in terms of say watts is known, say this function I can have the partial derivative of this. So I can know what shall be error in say force measurement if I am going to take the partial derivative of this complete function with respect to force measurement. So this value is known and this also is known. So you can anticipate what shall be the error into the force measurement, right? So this can be say considered here by taking some example. Let us consider the measurement of the power is to be done with 0.5% of the total accuracy. So this is now known. I am going to restrict my overall system uncertainty being propagated not more than 0.5%. Let us assume 0.5%. Then the allowable error on the individual factor will be given for the same example. Say for example del f, uncertainty into the force measurement, will be, say this is the power that we have measured and this is what is the inaccuracy that I am going to permit. So this is nothing but the value that is known. There are 4 factors involved into this, and then the partial derivative that we found out with respect to force of a function with respect to the force measurement is 0.29. So it means that del f should be restricted to 0.025 pounds. Same is the case with the radius measurement. This is the predicted error or the limiting error. This is what the total horsepower that I have found out. There are 4 factors involved into it, and the partial derivative of the function with respect to the measurement of the radius is numerically we have found already. So it means that it is 3 times, 3 values, that is inches, the measurement of the radius in terms of 0.3 radius. Like there is a measurement of in the length, error in the measurement of, this should be inch. Unit is inch, right? Then length measurement error is not more than 0.039, and measurement of the time we should not have error more than 0.15 seconds. Now let us compare this with respect to the earlier, the way we have started for. We have measured that time equals to say 1202 seconds. With respect to that 60-second time, we have got this as the revolution 1202, and there was a plus minus 1 revolution, right? So in this one, the accuracy of the revolution measurement is say 3, there can be error of 3 revolution plus minus, whereas we have found 1. So this was more accurate than that is required if we were to achieve 0.5 as a total accuracy of the system. Then on the force measurement, we earlier has measured force equal to 12.12 pounds, and there was possible error of plus minus 0.04 pounds. Now we have to tighten this. It means that we cannot permit error in the force measurement greater than 0.025 pounds, so that the device is to be changed now. More accurate device is to be used for measurement of the force if we want to restrict the accuracy of 0.5. Then for measurement of the arm length in inches, it was measured 15.63 and plus minus 0.5 inches. Whereas now you can see here, this require more accurate measurement of the length. It was required with 0.05 inches as an error in measurement. Now to restrict or to achieve better accuracy, we must have control on the length measurement of the order of 0.039 inches. Right. So same is the case with the time measurement. The stopwatch that we used, or say accuracy in the measurement, was limited to plus minus 0.5 seconds. Now we should come down. We should be more precise in measurement of the time. It should be 0.15. Then earlier error was something as 4. Let me recall that from the expression. It was 0.49. Total uncertainty earlier we found was 0.49, and now it is required to have the total uncertainty propagation of 0.5. That is 0.05. They can compare. This is what we require to achieve. Right. So this gives the understanding how we can proceed for having the control over the inaccuracies on all the equipments. Now there are little practical difficulties. Say for example, on experimentation you have found that force measurement by assigning equal propagation of the error on all the devices or all the measurement systems, we have got these values, but it may not be visible all the time. Right. See, the more clarity in achieving accuracy here is in the length measurement. You can have a better micrometer screw gauge or something else which will be still accurate than this. So in actual experimentation, what is done? We try to find out the factors, the entity under measurement, which can have better accuracy. So we have better measurement devices, suppose for length measurement. So the most accurate one we select, and through which we carry on the measurement, and we can see that this error can be still lower. Now once this is still lower, it means that there is scope of having little more inaccuracy than something like 0.0254. Force measurement also is possible. Now revolution measurement, we can relax little more. And this is what is done in actual practice, because we cannot find out everything numerically, because the device also should be available. The measurement system also should be available with all the error sources that we have studied to this point of time. The random error, the systematic error, miscellaneous error, and the other sources like error because of the personal say factors, error because of the environmental issues. Right? All those sources makes the uncertainty measurement as a very limited function. So wherever it is possible to achieve highest accuracy, we go for having those instrument and those measurement techniques, so that wherever it is not possible to achieve the given accuracy or the given uncertainty, we little relax that. This is what is actually done in measurement practice. This is a very simple example. There are only 4 entities under measurement, but there are many issues where we cannot predict how the forces are, how the errors are going to propagate. So for example, I would like to catch your attention. So in your theory of motions, you have gone through a 4-bar mechanism. Say now I require to have a function here on the workspace that this point should reach very precisely at the given location. Say, for example, this is my desired location, and it should be, say, possible to have the motion so that it's going to reach this point very precisely with, say, plus minus 0.001 millimeter accuracy. Right. Now, in this condition, you cannot have any equation. In case of the power measurement, you have made the equation of power equals to, say, twice pi into 60 as a very standard equation in terms of watts. It is not possible here. In actual machines, say you take example of any machine like turning machine or some other machines, the accuracy of the force measurement or say accuracy of the power measurement becomes little inaccurate, because there are many factors, known, unknown factors are there. So in this one, we do not have any formal relationship here. So we need to go for different approaches now, which are more similar to the method of say equal effects, method of equal effects for the accuracy prediction. Right. So this, we can consider that this is another experiment, experiment B. Experiment A was measurement of the power, which was very clear, defining the correlation between the different terms. The speed, the torque is related with n times t by 60. This was the simple relationship. That's what we have derived the factor k, and then we have written that in terms of the k. But it's not possible here. Same is the case with the different manipulators. Right. So relationship is not, whenever it is not defined, then it becomes very difficult to get the accuracy in the measurements. And that is why we are now switching over to the different measurement methods. I will give another example of a coordinate measuring machine, the 3D imaging machines or 3D imaging techniques. So instead of having the mechanical instruments used for knowing the values, say I will just give the idea. Say now this is a workpiece and I want to know the dimensions of this. The normal method is I am going to measure this and find it out. But if I am going to have a 3D imaging machine or 3D imaging technique I am going to use, I will have the different light rays passing on this, and with the help of imaging technique I can know what is the depth of a particular entity or a particular curve that is generated on this particular object. And then I will have very precise measurement where there will be less chance of errors being propagated. I think I am trying to catch you in some different domains. Yes, because this is very important from the measurement point of view, from the exact status, knowing exact status of the given system. Right. So I think few simple examples are given in the textbooks. You go through the textbooks. There are different examples given for these uncertainty propagations. Okay, so those can be referred. Any doubt into this? Now, just something else to be discussed here. Again, I am catching your attention that this is a static measurement or the static error calibration or the static property of the measurement device. Here we assume that the number of revolution during the test time is going to remain constant. The force that is applied for the given say speed is going to remain constant, and so on. Right? But if there is some change in the input, say for example revolution is going to change, they say there is a wide fluctuation to the voltage and current of the given supply for the motor, then motor will exhibit some different properties, like it will have change in the revolution per unit time. For first 10 seconds it will have some different revolution, and for next 30 seconds it will have some different speed of rotation. Right? So these variations are not considered. So this method of equal effects and say uncertainty propagation, the Taylor series expansion or other earlier element that we have studied, those are more or less valid for the static property measurement. But there are many situations where we need to encounter with the change in the input for each and every individual entity under measurement. Right. So I think we'll, in the coming classes, we'll see the dynamic properties of the system and then how to proceed for the dynamic characteristic measurement. But let it be very clear to you that the dynamic characteristic measurement is very difficult, and practically we say that it's very impossible to know how the system is going to behave. Say for training purpose, what we can do is a system, if it is known completely, we can give some standard known value to it. It's a very standard process. You recall the process of calibration into the deadweight pressure tester or some other way where we are going to calibrate. What we do is we apply a very standard, very precisely known entity, and then we compare the effect that is produced by the system, and then we balance that, and we know that the system is at this stage. There is a null balance technique, or say deflection technique, or we say calibration. But it's very difficult to calibrate for the dynamic system, dynamic characteristics of, right? But still we try to know the performance of system for some criteria. So I think we'll carry out the discussion on this in the coming class. So I want to conclude here for the static characteristics measurement or the prediction of the static characteristics. Now you can refer all the textbooks which are possible to you. Try to find out more and more example based on the static property estimation. In your test number 3, what we are dealt with is a very simple measurement where there is an experiment carried out for some variation in the input. What is the response given by the measurement device? So there is one minimum value, there is one maximum value, and so on. And then you anticipated the simple say characteristics. But similarly, I think we have discussed regarding the shift over of the sensitivity, that is the bias and the sensitivity drift, that can be anticipated. Then with the help of random measurement, we can anticipate. With the help of regression analysis, we can anticipate what is the change in the linearity, what is the change in the hysteresis, and so on. So I think we'll propose one more test on the static characteristics there, and then we'll come with the problem on the uncertainty propagation. So one test on the drift and other estimation of the static property. One more on the static property, that is uncertain propagation. One test can be planned, and then one test on the dynamic measurement. So I think 3 or 4 more tests can be planned. Okay, so I will confirm. I will let you know what is the portion and what is the test to be conducted on that particular portion. Okay. So any doubt here? Anything you want to discuss? Now please go through the textbooks, and if there are any doubt, it is highly possible that you are having some doubts in your mind, so that we'll be able to discuss it again. So before start for the dynamic characteristics, let me know any doubts or any difficulty in understanding the static characteristics portion. It may be possible that because of the limitation of time or space, something I might have skipped something, or I might have jumped say on the different steps. So please go through and let me know if there is a doubt. We can discuss that in detail here. Right. So with this note, I think I will stop here for today. Now I have given you instruction for submission of the journals, practical journals, that is submitted in the group. Say for example, group 1-1 consisting of, let us say, 4 students or 3 students. So they will make a journal in between, as I say, they will submit as a group. Right. I hope that you have followed the deadlines. If you are not submitting that on time, that will be given late mark. So for example, 5 marks for timely submission. The student who are submitting late, the group that is submitting late, will get, say, 2 marks less. They will get only 3 marks. And then Viva will be conducted. Some marks will be given to Viva. And then we'll have the assessment of your practical work. Right. So you follow you follow the deadlines. It's not happen that you are going to lose the marks unnecessarily because of making it late. So I think I'll stop here for today. Thank you for joining.